Hello, it's been a long time, but we are finally up to the last few videos of this series. And we are assessing the limitations of the Rutherford and Bohr atomic models. So first, Rutherford's model. He discovered, or he and his colleagues discovered that the atom was made out of a dense nucleus that had electrons on the outside. And he assumed that the electrons must be orbiting around the nucleus, kind of like how planets will orbit around a star or the sun. Um, so in any kind of orbit, which is uniform circular motion, there must be some kind of force pulling towards the center. In this case, that force is through the electromagnetic force from the negative electrons attracted to the positive protons. And he thought some kind of sideways velocity. So force inwards, sideways velocity, what does that give you? That gives you an orbit, uniform circular motion. So what are the limitations of this idea? Well, charged particles are connected to, and in some way they are, what creates the electric field, right? So these are electric field lines that are all connected to this electron, okay? And they should get wobbly around here because of the positive charge in the middle, but let's ignore that. So this electron, as it spins around and around this nucleus, right, as it goes around and around, these electric fields, they're going to be also moved around and around, right? The electron is holding onto them. So as it goes around and around, they're going to swing up and swing down like a wave, just as if I was holding onto a piece of rope and I moved it like this around and around, the rope's going to send out ripples, right? Or if I put my hand in water and I spun it around and around, that's going to send out ripples of waves. Of course, when you get an electron and you accelerate it back and forth, you create electromagnetic waves. If you do the calculations, which is not that hard, you find the radius of an atom, say a hydrogen atom, you work out the force, you can calculate that without too much difficulty. You can work out using the circular motion equation exactly over R. You can work out exactly how fast the electron is going, what its period is, and if you work out its period, that's going to be the same period as the wave, and you can work out its frequency. When you do that, you find that atoms should be releasing X-rays. So this green wave that I've drawn here, coming out that way, should be X-rays, and it's the electrons losing energy to create those X-rays, right? As they come out, the electron loses energy. What type of energy does it have? Well, the electron has potential energy being held away from the nucleus. So if you drop it, it's going to crash into the nucleus. So it has that potential energy, and also has kinetic energy from its motion. So if it's losing those two, that means it's getting closer to the nucleus. And really, it's releasing so much energy because X-rays are very high in energy. It's losing energy so fast that almost in an instant, the electron should just spiral down, crash into the nucleus, causing the whole nucleus to collapse. Now, this doesn't happen. Obviously, it's a big limitation of Rutherford's model. Electrons don't collapse into the nucleus. Atoms are stable. Atoms aren't just releasing X-rays all the time. So something about Rutherford's idea of orbiting electrons is very, very wrong. So Bohr, well, you'd say Bohr fixed it, right? Not really. One of Bohr's postulates just was that electrons are in stable orbits. End of story? Not really, but that's all that Bohr said. So Bohr said, yes, an electron is orbiting the nucleus of an atom. For some reason, I've got a hydrogen-3 atom, helium-3, sorry. Yes, the electron is orbiting it, but it is stable. It cannot lose any energy. It exists in that state perfectly. Did he have a reason for this? No, he didn't. So that's a limitation of Rutherford and Bohr's model. They can't explain how electron orbits are stable. But Bohr said some other really useful things, because he said that each each shell that the electrons can exist in is specifically linked to a certain amount of energy. Okay, and this is the same as thinking about gravitational potential energy. Again, there are fields electric fields creating forces on these charges. And if you grab the charge and you move it further away from the center, that increases its potential energy. So it makes sense that the bigger the orbit, if the electron is up here, it has more energy, more of that potential energy. And if it's in a lower down orbit, it has less energy. Okay. So he said that electrons exist in shells that have certain amounts of energy. Now, he also said that these shells are in very specific positions, or that they have very specific amounts of energy, and that electrons cannot exist in areas in between. So if this is the first energy level allowed, and if this is the second, and if this is the third, then any electrons in positions not exactly in those three shells, but somewhere in between, they cannot exist. They are not okay. Instead, electrons have to exist on the shells. Okay. Cool. Now, electrons can go in between shells. This is where. Okay. So we have to talk about the quantized energy levels of the hydrogen atom. Quantized mean they have specific numbers. These are the shells. The shells are the specific amounts of energy that electrons can have. As in the quantized energy levels, we're talking about the shell 1, shell 2, shell 3. Those are the quantized energy levels of the hydrogen atom. Let's change this to a hydrogen just so that we're talking about the same thing. Brush just a single proton in there. Beautiful. Okay, and the law of conservation of energy. So there was this phenomena called the absorption and emission spectra. Here's the spectrum. Let's put it here. Right, it's this phenomena that people knew about, but they couldn't explain, and Bohr's model explained it perfectly. It's really, really good. What had happened was this: in hydrogen, if you give it energy, it can start to glow. And if you give it the right amount of energy, it glows in these very specific ways. It glows just with these exact colors, right? And from Planck, we knew that exact frequencies of light, those photons have a certain amount of energy, which we can find using Planck's equation, E equals hf. And so Bohr connected the energy of the photons coming out of hydrogen to the energy of the electron shells in hydrogen, right? He connected these using the law of conservation of energy. He said that if an electron that has a lot of energy jumps down to a state where it has less energy, where does that energy go? It leaves in the form of one of these photons of these specific colors of light. Why are they specific? Because the energy levels are quantized. They are specific themselves. So quantized energy levels, if you jump from one to another, you release an exact amount of energy in terms of light, and that exact amount of energy must be a certain frequency of light, which for this jump here from the third to second shell happens to be this red line right there. Okay, genius, really, really good. A couple of guys later then worked on trying to figure out the mathematics of how that worked, came up with this equation here, which says if you jump from a certain initial shell, that's Ni initial, down to a certain final shell, Nf, and you do some math and combine it with a constant, the Rydberg constant, which is in your data sheet, then you can work out the exact wavelength of light that comes out. And of course, from wavelength, you can calculate frequency. You can do it through these equations if you want to, or just through the normal wave equation. Now, Bohr's model still had limitations. One, he could not explain why the shells were stable and why they were quantized. He couldn't explain that, which we already said. Two, however, he also was combining ideas in classical physics with the new quantum physics, right? He said that, yes, the electrons are orbiting, and that's through orbital mechanics, the forces holding them in place, but also that the energy levels must be quantized. And these two ideas, quantum physics and classical physics, have different foundations, and he's basically just cherry picking the parts that work to explain the phenomena of spectral lines without really, so without a solid base, there's definitely something wrong with his model. You need to convert completely to quantum physics or completely to classical um, for it to make any sense at all. Okay, and now this middle dot point here is asking us to talk about the line emission spectra, so these lines here, to examine the Balmer series in hydrogen. So the Balmer series are all the jumps from levels higher than 2 down to 2, or 2 to higher levels. So 3 to 2, that's the, what am I going to use, purple. 3 to 2 is the line down here, this red one. 4 to 2 is this blue one. 5 to 2 is this purpley one. And 6 to 2 is this other purpley one, right? The higher the jump, so say 6 to 2, that's a big jump in energy, means you're releasing a fat photon with a lot of energy. That's these high frequency photons here. Remember, high frequency means higher energy. A lower jump, such as jumping from 3 to 2, only one shell difference, that makes a lower energy photon like this red photon here. If you want even smaller jumps than that, say go from 2 to 1 or 3 to 1, those are smaller jumps, then you go even further down into the infrared. If you want even higher jumps than our 6 to 2, you can go from 4 to 3. Sorry, I got that the wrong way around. If you're jumping down to the first level, that's a high amount of energy, that's a big jump. You're going to be releasing ultraviolet light. If you're making smaller jumps, such as jumping from, say, 4 to 3, you're going to be releasing less energy. That's infrared. Okay, hopefully that all made sense to you. Have a good one.